Welcome back, everybody. In this next segment in chapter 19 about aldehydes and ketones, we're first concerned about hydrolysis reactions. So here it's the hydrolysis of acetals, and then there are a couple of segments where we go back to analyzing additional nucleophiles, including sulfur, hydrogen, and carbon nucleophiles that add more complexity to this chapter and adds more functionality, or I should say more tools into our functional group interconversion toolbox. Okay, that was a mouthful. Let's move on. So when I see the word hydrolysis, I like to remind myself of lysis, L-Y-S-I-S or E-S for plural, that this has to do with breaking a bond or cleaving a bond. So in other words, we are now getting rid of segments of a structure. Acetals can be hydrolyzed using aqueous acid. Here we have our square brackets with a proton to yield a ketone and two equivalents of alcohol. So in this case, we kind of have a balanced equation. Our two carbon-oxygen single bonds in this acetal, that's our pattern, and we'll talk about this a lot when we get to chapter 24, carbohydrate chemistry, will be converted to the ketone, and then whatever the R group is here, we have 2 moles of these alcohols. Basically, we're reversing the acetal formation. So there are schemes in your textbook, and we also covered some of this in the slide deck. So the other thing I want to point out here is that these conditions here are really pivotal, because when we have basic conditions, Na plus and OH minus, this will not budge, this will not react. And this is also true for, let me actually quickly draw a structure. We can do reactions with a commonly known solvent that you encountered in Orgo 1. It is a 5-membered ring with an oxygen, and it's known as THF, tetrahydrofuran. Basically, you have an ether bond here, and this also will not react with bases. This can only be activated once we have a proton in our reaction mix, where the oxygen here is being protonated. We can think of the same way in these structures, that the first step has to be interaction with a proton. I'm just going to pick one of these. I also encourage you to draw all non-bonding electron pairs, because you might get confused about resulting charges later on. We need one electron pair that is going to then attack that proton. Basically, I'm pointing out patterns. As with this cyclic ether, we're doing this with what looks like an ether, but because we have 2 of these OR groups attached to the carbon, and now has this fancy name and is called an acetal. So acidic conditions, no basic conditions, because it's not going to work. And we have that insight on a molecular level to understand when reactions work or not, and mechanisms are our friends, and we can make sense of all the electron flow that is ongoing. So here, surprise, surprise, this is how it starts out. You may want to pause here. I will not go into too much detail here. I trust that you can work through this to understand proton transfer, loss of leaving groups, so on and so forth. One thing I would like to show here is that technically an H plus does not exist. An H plus is part of a hydronium ion, and it's drawn here properly, but the net transfer of a proton is shown in the structure. So I sometimes like to just basically draw H plus instead of drawing all of H3O plus. We go from the acetal to half an acetal called hemiacetal, sequence of steps, to now the ketone. Hydrolysis of imines and enamines. Imines are easier than enamines. Imines, basically squiggly line, this is where we break the bond. We go from carbon-nitrogen double bond to carbon-oxygen double bond. We do the reverse of what we learned from previously, primary amine, ketone to imine. Now in this case, it can be a little bit more confusing. Remember that this goes through an ammonium ion. So we have a double bond here. And if we think about that the precursor to this ene, double bond, amine, is, let's draw this quickly again. It was the carbon-nitrogen double bond, R group. I'll just fill in the R group. Don't forget the charges, always analyze the charges. And if I now think about, oh yeah, the enamine comes from this bonding pattern here, I do the same thing as up here. And now I see, yeah, that's just going to reveal a carbonyl group. I know that. So, and here as well, it's simply the reverse of their mechanisms of formation. And you can practice this also with Skill Builder. Now we want to continue our pattern recognition. We're going to switch back to a forward direction where we are functionalizing the carbonyl group into other groups. So we had learned about acetal and hemiacetal with oxygen nucleophiles. Well, what's underneath oxygen? Sulfur. It's bigger, but we can do very similar chemistry. Ketones and aldehydes both react with what is now called thiols. Remember before we had looked at reactions with alcohols? Well, there is a new word here. It's called thiols. So instead of having the OH group, we have an SH group. There's very similar chemistry. We want to recognize that we're using acidic conditions. Here again, we're using acidic conditions. The two R groups can be coming from two molecules or one molecules in which the two SH groups, the thiol portions, are tied up. So it's really all very similar. Now, instead of saying this is acetal and hemiacetal, we're actually referring to this as a thioacetal, indicating that the oxygen has been swapped out with a sulfur. And this, as we've seen before, is also a condensation reaction as a molecule of water forms in this process. Thioacetals can then also be further converted. It's a little bit similar to what we learned from ketone to a hydrazone and then elimination through a Wolff-Kirschner mechanism. So we're basically replacing the two carbon-sulfur bonds with two carbon-hydrogen bonds. There are very specific conditions and the reduction method. So this is taking down the oxidation state on this carbon is called Raney-Nickel. So we now have another method for reducing a ketone or an aldehyde to the corresponding alkane. We had seen this one before using a nitrogen intermediate. In this case, we have acidic conditions, this thiol, and now under the second reduction conditions, we're replacing a carbon-oxygen double bond with two carbon-hydrogen single bonds. Thus, this is a reduction reaction. All right, let's look at some other nucleophiles. Hydrogen, most of the time we encounter it, is just a naked kind of atom and carries a positive charge in the form of a proton. Now, very different deal here. We can talk about hydrogen as a nucleophile because there is also a hydride structure. Remember that hydrogen is main group number 1. It has 1 electron. In most cases, it gives it up and then carries a positive charge. But we have ways of generating a hydride, which means there's a second electron. With it comes a negative charge. Please recognize some of the reagents that you already encountered in Organic Chemistry Part 1. This is lithium aluminum hydride, LiAlH4. This can also be abbreviated with a TLA, a 3-letter acronym, LAH, so you might find that over the reaction arrow. And then there's a second reagent, sodium borohydride. We'll encounter this later on as well with other functional groups. So it's important for you to recall what this is about. So it's a hydride delivery reagent, whether it's lithium aluminum hydride or sodium borohydride. Net effect is both of these will get attacked by a hydride. We want to draw in our electrons to understand this. We had seen that this is delta positive. This, of course, is a full negative. We know how this is going to go down. For the first conversion here, reduction condition, it's a 2-step process, but we can also, and it's a harsher process. For the second step, we can use a milder process. In the end, we are going to get from a carbonyl group, ketone or aldehyde, we will get an alcohol. Just depends on what these placeholders here have attached. These reductions are carried out under basic conditions. Remember the differentiation at the beginning between acids and bases. Hydrides are strong nucleophiles, and we had encountered them before as Lewis bases. So here we see the process. I would accept a mechanism that just uses a hydride, and then we see that H- is going to attack the carbonyl group. Technically, the hydride doesn't just swim around in your solution. We have these two electrons tied up in a bond to aluminum. So this arrow indicates that both electrons move over here. Of course, we have to then break the bond to oxygen, forming this tetrahedral intermediate. It's a very important intermediate. We have to make sure we follow the charges, negative charge here, second step, proton transfer, and here we are with an alcohol. If we have unsymmetrical ketones, we actually form a new chiral center. There are different words used for chiral centers. Remember how you looked at carbon atoms with 4 different substituents, talking about enantiomers, later on about diastereomers. So this was all material in your stereochemistry chapter, titled Stereoisomerism, chapter 5. We won't get into too much more of this until we hit carbohydrates and amino acids towards the end of the chapter. Just a quick overview, 2 different substituents, an ethyl group versus a methyl group. It's an unsymmetrical ketone, the 2-step procedure. We're essentially getting an alcohol. And now we have here, remember how you may have placed asterisks to indicate where your chirality center is. Again, these can also be called stereogenic centers, asymmetric centers. There are many different terms out there. This book uses chirality center. You get a mixture of 2 enantiomers that are termed racemic mixture, because there's a 1-to-1 chance that either one of them is formed, depending on how the hydride attacks. It can attack from a top phase and from a bottom phase, and thus we have this stereochemical outcome. Then we have also in here carbon nucleophiles. Let's go with pattern recognition. Grignard, sorry, this should be capitalized because it's named after a very famous chemist who came up with this very important method to make new carbon-carbon bonds. Synthetic chemists get really excited when a new carbon-carbon bond can be made. Better yet, when 2 can be made. Anyway, we're sticking with 1 here. I had emphasized that you can think about Grignard reagents as essentially a common pattern with R, Mg, magnesium from main group number 2. I'm going to use a different placeholder here because it can be an X. And how we can think. So I'm going to use quotation marks here, but this is a delivery system for an R-. So you're going to have to draw an electron pair. There's your nucleophilic character. Where is it going to attack? Ding, 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 ding. Delta plus, we've seen it before. The second step protonates, and here we are. We made an alcohol. So you've already covered alcohols from the other side here in Orgo 1, and that was chapter 12. And we can do the same here with an aldehyde. Again, a net methyl anion that's attacking, then being quenched, and here you are. And remember, if it's something unsymmetrical, you're going to get a racemic mixture. Racemic mixture was image, a mirror image. Look at your hands. There's a certain reflection relationship between the 2 structures, the 2 mirror images. So either phase of the carbonyl group is attacked, and so we can form a new chirality center. Could we do that with this one? No, not really. Why? Because we have some internal symmetry. Also something that we had analyzed over and over again, especially when we looked at proton and carbon NMR. And of course, these were discussed in previous chapters. As we're moving on, so here you can pause. I already gave all the words to this. You can work your way through it and then practice with, a question in the conceptual checkpoint category. If it's all clear to you, you can move forward. I know that some of you are doing really well. And pattern recognition becomes a lifeline, especially as we face a lot more information, and then holding this large body of information with really abstract concepts, holding that and making sure that we move down the right conclusions to come up with a good answer. Now, in the carbon nucleophile category is also cyanide. Cyanide, which is toxic. We are dealing here HCN. Remember, this is a very strong acid. Can be dissociated into H plus and Cn minus. If we wanted to draw this out here, remember we have a carbon-nitrogen triple bond. I'm filling in the other electron pairs, a bit faint, but here it is. Neonucleophilic site. Where would it attack? It takes 2 to tango. Nucleophile, electrophile. It always comes back to 2 to tango. Nucleophiles, electrophiles, delta minus, that's where it's gonna, delta plus, that's where it's going to attack. And in this reaction, it's a little bit similar to hydrate and acetal formation. We are converting the double bond into 2 single bonds. When we made the hydrate, it was 2 OH groups. Now, we're actually introducing a cyano group, thus we now have another technical term. This is called a cyanohydrin. So this reaction works better under basic conditions. Well, it's very clear, because if you have fumes of this, it can literally kill you. And so we're using a catalytic amount of base in this reaction. Again, here you can work your way through. Pause the slide. I will move on. So, looking at the cyanohydrin formation, basic conditions, we use actually KCN. KCN is a delivery method for introducing the key ingredient, which is Cn minus, right? So this dissociates Cn minus. It's akin to the structure I had shown before. The nucleophilic portion is on the carbon with the free electron pair. And here you go. Carbonyl group, double bond turns into 2 single bonds, one to an OH, the other one to Cn. Pattern recognition, ketone to aldehyde, same deal. Carbonyl group becomes hydroxyl group and cyano group. This is unsymmetrical, so we get image and mirror image. 2 enantiomers we call racemic mixture in this transformation. And in the cyanohydrin formation, the installation of the cyano group now gives us another tool for functional group interconversion. So here's a follow-up. We have now a cyanohydrin, carbon with an OH group, carbon with a carbon triple bond nitrogen. So there is a mechanism to this that you can work your way through. Remember how these conditions here, basically we have H minus in our pot. With it comes a free electron pair, it's a Lewis base and a nucleophile. And to understand what is going on here, think of this hydride source as reducing the functional group. What does this mean? We decrease the number of carbon-nitrogen bonds. We had seen it before. If we have a carbon-oxygen double bond, we can reduce it with hydride to single bonds. So we're doing the same thing here. We're adding basically hydrogens. There are 2 hydrogens on this carbon that is shown here. And we've now added 2 hydrogens here. Okay, so we've added twice, technically, 2 moles of hydrogen to reduce it all the way down. No more double bond. Okay, maximum number of hydrogens. That's another definition for reduction reaction. And then the second one is also going to be very helpful. We'll look at this again when we get to our carboxylic acids, which is chapter 20. So we'll get a different view from that functionality standpoint and a lot of additional chemistry. The way I like to think about this, because even when I was a student, I struggled with do I just memorize this? What does it mean? For me, it helped to think about the conversion of the nitrile group which has 3 carbon-nitrogen bonds, to now think about, oh, this turns into 3 carbon-oxygen bonds. Okay, so in this case we have a double bond and a single bond, but it's still 3 bonds to oxygen. So that could help you remember this additional functional group interconversion.